Okay, so I'm going to go through Lab 8 here and try to cover all the techniques that are in the lab so that you can use this video as a reference as you're working through it. Okay, so this first page is mostly just definitions and things that we've talked about before, so looking at the hinge line, the fold limbs. So go ahead and use the internet, Google definitions and stuff, use your previous labs or the class textbook online. You'll find all the stuff there really clearly laid out. I'll highlight that you should talk about the Younging direction on the two questions about anticline and syncline. So, that means that, well, we all basically know an anticline looks something like that. Also indicate which side of the anticline is younger and older rocks. You can do that just by saying young and old. Some people draw an arrow from old to young to show the Younging direction. Okay. So, getting into the maps. The first map doesn't have a lot on it, but that will change once we go to town using some structure contours. So, question 1 says, map 1, at locality B, 100 meters above sea level, we find limestone unit dipping 45 towards 240. At outcrop A, 200 meters above sea level, this unit has a dip of 65 degrees and dips towards 344. So, the first information we've got is the elevations of the two locations. So, B is 100 meters above sea level, and A is 200 meters. Now, we are going to assume there's a fold present in the area because these two locations are representing the same bed at different orientations. So we have to assume that bed is folded in order to accommodate both of those orientations. So the first question asks, construct on the map the intersection of both limbs at the 100-meter level using structure contours. So basically we just got to add some structure contours here. I'm going to get my ruler, and our first structure contour, if we remember back, the definition of a strike line is a horizontal line on our plane, and the definition of a structure contour is a horizontal line on a surface. So a strike line and a structure contour, or any contours, is the same, at least locally. So we're going to treat each of our limbs as planar features, and I'm just going to expand our strike line into a structure contour. And we know that B is at 100 meters, and so that tells us that this is at 100 meters. It's our 100-meter structure contour for limb B, I'll say. A, do the same thing, and that's going to be our 200-meter structure contour for limb A. Now we need to be able to add more parallel, regularly spaced structure contours for each limb, but we need to figure out where we put them, what the spacing is. And previously we went from using the spacing of structure contours and turning them into a strike and dip, getting the orientation from them using a trig triangle, and now we're just going to flip that process and start with our dip and go to the spacing. So to understand that, I'm going to clarify two terms I use when talking about contours. So there's contour interval and contour spacing. The contour interval is the difference in elevation between adjacent contours. The contour spacing is the map view distance between adjacent contours. So if we have our map here, The interval would be what elevation our next contour is at. So if we make it a 100-meter contour interval, then our next contour here would be at 100 meters, down from 200. The contour spacing is the map view distance. It's this distance in map view that we put our next contour at. So if we cut a triangle across our structure contours by looking in cross-section, the dip of our unit, or our bed in this case, is given by theta here. The contour interval is this vertical distance so long as we're using two adjacent contour lines, and this distance here is the spacing. So we can define the contour interval to equal 100 meters. We know the dip from what's given in the problem, and so we can calculate the spacing. So, for example, the 45-degree dip at B, that triangle would look like, I'm trying to make this look like this. The angle is 45. The interval we're going to say is 100 meters, and we want to know what this distance is. You can already tell, just by looking at this triangle, that it's a special triangle. 45 here means this is also 45, and that means that these two sides have to be equal. So in this case, x equals 45. I'm sorry, x equals 100 meters. So the spacing in the interval, in the case of a 45-degree dipping bed, are going to be the same. It gets trickier when we look at the 65-degree dip. At A, that triangle is going to look more like, it's going to be even steeper. Perfect triangle. Okay, so now it's 65. And if we keep our 100-meter contour interval, then our spacing is going to be different, and we have to set up our tangent function. Tangent 65 equals sit over adjacent 100 over x. And you can solve this for x to get spacing. The final step to getting our new contours on, once we've got this spacing, is that this is in sort of real-world coordinates, 100 meters. So we need to use our ratio scale, which says that 1 meter on the map here is 4,000 meters in the real world. We can use that to convert our 100-meter spacing for the 45-degree dip into how far it should be a ruler on the map. So what we do is 100 meters divided by 4. You can tell that you should divide because we know you should get 100 meters. We could not 100 meters paper. So we're going to by dividing it by 4,000. If you multiply by 4,000, you'll end up with 4,000 meters, and that doesn't make sense. We get 1/40 of a meter, and meters are awkward as centimeters and inches, but we don't use inches. So I'm going to multiply by 100 centimeters per 1 meter. Cancel those meters. It's one of the tens. So it becomes 10 divided by 4 centimeters, which is 5 centimeters. So for B, we're going to put a contour every 2.5 centimeters. And importantly, we have to label our contours. So we had our 100 meter. We're going down this way according to the little diptych. So this is going to be 0, negative 100, negative 200. This way we'll go up 200 meters, 300 meters. meters. So you should repeat everything I just did using the spacing you determined here for the 65 dip, and set a bunch of contours running this way, parallel to our A limb. And once you've got them, you're just going to find intersections of those two limbs. Remember, the intersection of the two limbs of a fold is the fold axis, the hinge line. So we've got one intersection on here because we've got our 200 meter contour and our 200 meter contour, and they intersect right here. And you can imagine that the 100 meter is going to intersect somewhere in here. So I'm not going to use the real spacing. I'm just going to draw in some contours so I can show you what to do with the rest of the problem. Yours will be perfect and correct. Okay. So if this is the 100, 0, negative 100 contours, then the intersections become 100, 100, 0, 0, negative 100, negative 100, and they line up nicely. So this line of intersection is the line of intersection of the two limbs, and it represents our fold axis. So the question asks, well, first I can address one. Construct the map intersection of both limbs at the 100 meter level. That is just asking us to highlight the fold everywhere it is at 100 meters. So I'm just highlighting this line. 100 meters until we hit the fold axis and we switch limbs to limb B, and we go to those structure contours. So there, now I've highlighted the fold at 100 meters, sliced at 100 meters. Okay, to find the trend and plunge of the fold axis, what you need to do is make another triangle. We've got a fold axis running along here. We might be able to intuit that since this limb B is tilted down like that, and limb A is tilted down like that, then our fold axis will be tilting down to the northwest. So what we're going to do is draw a triangle, and the triangle we want is between two contour intersections with our fold axis. So we'll use these two and draw the cross-section triangle looking from the side of these two. This one's at 0 meters, this one's at negative 100 meters. And so when we draw that, we get 0 meters, negative 100 meters. Here's our two structure contours. This is a cross-section. I like showing a little person for that. We're curious about the plunge of this line, theta. We know that this is 100 meters, the difference in elevation between the two contours. And we can measure the distance along the surface. And the way you do that is measure, I recommend centimeters, the distance between them. So remember, your value might be different because I've just drawn this without being precise. But mine's about 3.5 centimeters. And so you take that value, 3.5 centimeters, you multiply by 4,000, the ratio scale, and you'll get something $14,000 and centimeters. So then I can multiply by 1 meter per 100 centimeters and get 140 meters. So the spacing here for me is 100 meters. Yours will probably be just a little bit different. So this is 140 meters, and now we've got everything we need. We can do tangent of theta equals opposite 100 over adjacent 140, 40. And we can solve this with a tangent inverse for theta. So, finally, the trend of the fold axis is just the azimuth relative to north. So remember that the direction is in the down plunge direction. So if you want to look at something northish, and so the angle you want to measure is all the way around to there, from north. Finally, it just asks to plot both the limbs in stereographic projection and label the fold axis. This is for you to check that the stereo agrees with the answer on here. I realize most of you don't have it, but if you grab your stereo net and plot it up just by hand right onto this, just approximate it, you should get a similar answer as you've been getting on here. Okay, that's map 1. Map is a little bit more work. So folds are among the most common structural features in geologic maps because they are responsible for designing but complicate map patterns. A deal fold on geologic is very similar format to what we've looked at in Lab 2. So contour the and lower surface ruled bed shale. Ruled bed, we mean texture here. It's this winding sinuous of hill. The fold is like a shale unit. So that means as we structure or contour our shale unit, we would expect them to all be parallel and regularly spaced. Okay, report the strike of the folded shale unit. So since all the strikes are the same, we can give the strike value for all of them. So, looking at this, is that too close? No, that looks good. We've got a lot of places we could start contouring, and eventually we're going to fill up this entire thing with contours. An important thing to understand is that you might say, okay, here's a contact for the shale unit, and I see that it's at 500 meters here and 500 meters there. So why can't I connect those with a structure contour? And what you'll find is if you continue with that logic that the structure contours are oriented approximately like this, you'll quickly see that it becomes impossible to fill out the structure contours. As soon as you go to the next contour here, where you connect it over here, this contour loops around here, so it doesn't make any sense. We're looking for matching points where we can connect a structure contour and have them all be straight and parallel, all the structure contours. So if you look for a while and just try different options, you'll see that this point here is at 500, this is at 500. If we line those up, we also see that it crosses here, and hey, it's at 500. So it's starting to work. Okay, so I'm going to fill in a few of these. And I would recommend this. Start by just contouring everything, and don't worry about the labels as much for now. We'll label everything in a second, and we'll have to be very thoughtful about our labeling. Okay, so I've drawn all these contours just based on this parallel orientation and the fact that they have to cross everywhere a elevation contour, topo contour, crosses our contact. So now I could continue on. You could put one there, one there, one there, one there, all the way across. Also, this side over here we should contour. But first let's talk really quickly about the labels for these contours. I'm going to zoom out so I can put some labels on here. So a key thing is, remember in the question it says the upper and lower emphasized surfaces of the ruled bed of shale. The thing to remember is that if we looked in cross-section, here's some topography, our bed of shale is dipping. And so this is our bed of shale. It has a lower contact and upper contact. And as we put in just some elevation values here, so this is 100, 0, negative 100. We can contour the lower contact. There'll be a contour here, here, and here. And we can contour the upper contact. So, of course, in our problem, we need to keep track of whether we're on the lower or upper. So, to figure out which side is the lower, which side's the upper, we can look at one contour that intersects both contacts. So this one, for example. If I look at this contour, I see that on this contact, this edge, it's at 500. But here it's 500, 500. When it goes to the other contact, this right edge, it's down at 300. So that means that I would label this 300 for the lower contact, lower, than 500, which is the upper contact. So 500 refers to this edge. I can even label that upper. And this edge here is the lower. So we've now started to fill this out. If we want to just follow the upper contact, let's do the next one. So here on the upper contact, this contour is at 400. So we're going down this way. So this one is 300. This one will be 600, 700, 800. I don't have anywhere where this 800 intersects the the upper contact, but I'm just inferring that this is going to continue. Okay, we can label the bottom ones. They should have the same orientation as these, because in theory the lower and upper contacts of a bed are going to have the same orientation. So in that case we can check 300. This one here is at 400. So 500, 600, 200, 100. Great. So we've got labels on this side. All down here I'm going to label the lower contact, and here I'm going to label the upper. Now do the same process, but for this piece of the shale outcrop, and then also this. We've got this big gap in here that we're going to have to infer the contacts by marching in from each side where we do have information until we get to the center. I'll finish up this right side really quickly. Okay, so I've added in contours for this side. You can do the right side. And what we want to observe now is that the two limbs seem to change. We've got two limbs of a fold, first of all. They've got different. If you look at these labels, we see that the elevation is decreasing to the west, and then right here that switches, and we start going back up to the west. And so in this case, we've got a fold, a line centered over here, with two limbs. So before I move ahead, the stripe of these lines is, remember, contours have the same contours as strikes. You orientate. The second question is asking, please label the axial traces for all folds. Axial trace is the map view of axial, and it says where find our axial. We're just going to find the exact point, the exact line along which two limbs meet. So this limb's coming in from here, this limb's coming in from this side. We can see that they'll meet exact halfway between the 300 contours. So I've drawn in a line there, and I can label it as a syncline. Now, there's a few ways you can find these. If you add all the contours, they become relatively clear where they are. But when you work over here, it's a spoiler, but there's another fold over here, and you're going to have less information to work off of. So what you're going to have to do is do your contours for this far eastern outcrop, and then start marching in, alternating sides with the same contour interval. So you'll find the 800, 800, 900, 900, 1000, 1000, 1100, 1100, 1200, 1200, and then you'll meet somewhere. Wherever you meet, you're going to draw in that axial trace and add your symbols for syncline or anticline. Okay. On the attached graph paper, construct, not sketch, a cross-section through XY. You can ignore any apparent diff corrections. Okay, so X and Y are there and there. We'll connect them with a line. So we're going to do a cross-section through our map from X to Y. And we've provided graph paper if you've got it. And what I'm actually going to do is fold my graph paper. Line up the graph paper like this along the line and mark the ends, Y, X. Okay, so we're going to have a vertical axis and a horizontal axis. Work in pencil, then you don't have to make ugly mistakes like me. Okay, this is going to be distance, and the vertical will be elevation in meters. You can have different scales for your horizontal and vertical axes on a cross section. That means that you'll have vertical exaggeration. It's pretty common, but it actually is really helpful to avoid vertical exaggeration. So we're going to try to make it 1-to-1, meaning that our horizontal scale will be the exact same as our vertical scale, and it'll help us out later on. So to get that scale, what we can do is go up to our map scale right up here and take a look at how they compare. So oh, look at that, it's very convenient. Basically, this distance here is 500 meters. And so each small square is 100 meters. So I can mark that on here. And then, remember, since we're doing 1-to-1 scale, we're just going to make our vertical scale the exact same. The values we need are something around 0, it looks like, to 1,000, so I'll do 0, 5. So line up the top of your section with your cross-section line, and we're going to start with topography. We've done this before in Lab 1. We're going to use, ignoring everything else on the map, we're just going to follow these topo contours and see where they intersect our cross-section. So here's one, here's one, here's one, here's one. Okay. So this topo contour is at 600, and so I'll bring it down, right straight down the grid from where it intersects to 600, make a dot. This one is 500, so straight down to 500 meters elevation, put a dot. 400, 300. Oh, let's see. Oh yeah, we crossed back up to 400 here. So this is where it gets a little bit tricky. We've got two 400s. What we can see is that the topography is going down, and then it pops back up above 400 here. And what we can actually do is see how close we are to the 400 and the 500 contour to see where, sort of interpolate where the elevation is between them. So what I want to see is that we're pretty close to 500 right here. We're pretty close to 400 right here, and then we actually touch 500 down here. So this one's 500. We get pretty close to 400, and we get pretty close to 500 right here. So with these two, it's just sort of getting close to. We're going to connect up all of these, and then it kind of goes out between 400 and 500 here. So remember, don't cross the 700, because that would imply we've already crossed 700 and we haven't gone there yet. Great. Now we've got our topography, the surface, and we're going to go and add in our structure contours. So the way to do that is just to do the same thing, but now only paying attention to these structure contours. I'll start with the top surface, upper, because they're just visible up here. Okay, so 900. I'll do it in red, because then it looks nice. 900. Right here is axial plane, and so actually I'll just dot that in for now. And then we repeat, and we're going back up. So we've got the top surface of our bed, our shale bed. Now we're going to add the lower surface. And the thing to notice is just that our lower surface elevations are just 200 meters lower than the upper surface elevations. So at every point I put here, I'm just going to put another dot 200 meters below. Have accurately reconstructed precisely the cross-section through the topography of this bed. And all of this, of course, up here and up here has been eroded away. We're just sort of projecting it up into the air. But here is actually where it would be underground. And we can see where it changes orientation, and so we can locate our axial plane. And now that I'm feeling more confident in it, I'll draw on a line there, label it axial plane. And your job is to continue this pattern over and find the next fold over here. Okay. Plot and label the fold limbs, fold axis, and axial plane in stereographic projection. So once you've got all these, it's asking you to plot the fold limbs and the axial plane and fold axis on our stereo net again. And this already has your answers from problem 1, but just try to make it clear which one is which. So these are easy because they're striking north-south, so they'll plot right on here really easily. To get the dip, we could do a few things. We could do our old method of drawing a triangle across here, looking at these two elevations and making a cross-section triangle and finding theta. This would be some distance we measured, and this would be 100 meters. But we've already constructed a very precise diagram with no vertical exaggeration. And so what you can also do is use a protractor, if you've got one, to measure this angle right here. That's the dip of this bed. That is the dip of this bed. They should be about the same. All the limbs turn out to be dipping about the same amount. And so I don't have my protractor on me, so I'm just going to say that that's 25 degrees. Use whatever actual value you get. And so striking north-south, dipping 10, 25 degrees. We get a limb dipping to the west. That's like that limb. It can be helpful to label like west, east, just for clarity. Here's our 25 degree dipping to the east limb. And right here and here, technically, on both sides, because it's a horizontal line, is the intersection of our limbs, which is the fold axis. And our axial plane is going to go through the fold axis and split the limbs. And since both limbs have the same dip, it'll just be a vertical plane. So, straight up through the middle, through the fold axis, axial plane. Limb, limb. Great. Okay, hopefully that was helpful. I realize that normally I'm able to give a lot more feedback in class on all of this stuff, and so I know we just sort of are walking through the lab, but really focus on understanding these concepts behind going between a structure contour and a triangle to determine its orientation, understanding the relationship between strike and dip and structure contours. Those conceptual ideas that we're working with here are the important things we want to emphasize and that we're probably going to ask you on the exam. If you have any other questions, of course, email me and let me know.